In the fall of 2000, a plant liquidation auction was held in Sydney, Ohio, a small industrial city 40 miles north of Dayton. Population 18,000. The equipment being sold had been manufactured in that same building. Precision tool room lathes, ground lead screws, hand-fitted spindle assemblies. Machines that had been built to a tolerance standard of 1/10,000th of an inch, a measurement so fine it cannot be seen with the naked eye, only felt through a trained fingertip pressed against a rotating shaft. The company that built them had been in that building for 91 years. The auction lasted 2 days. When it was over, the machines were gone, loaded onto flatbeds and hauled to surplus dealers, to community colleges, to small tool shops in Ohio and Indiana and Michigan. The building was empty. The Monarch Machine Tool Company, which had equipped the finest precision tool rooms in America for most of the 20th century, had ceased to exist as an American manufacturer. Here's what makes that fact difficult to accept. 40 years before that auction in 1960, the Monarch 10EE tool room lathe was the most precise production lathe available in the United States at any price. It was also in 1970 the most precise production lathe available in the United States at any price. In 1980, still the most precise. In 1990 still. The machine had not been surpassed. The company had not cut corners. The spindle runout standard held to 0.0001 inches. Since 1937 had never been relaxed. The precision that Monarch's assemblers hand-fitted into every headstock bearing had not been replicated by any competitor at equivalent cost. The Monarch 10EE did not lose because a better machine replaced it. It lost because the market stopped caring about what made it irreplaceable. But the real story of Monarch Machine Tool is not the auction in Sydney, Ohio. It is the story of what precision means in American manufacturing and what happens when a company builds a machine so durable, so accurate, so fundamentally correct in its design that the machine itself becomes the company's most formidable competitor. It is the story of a tool room standard that lasted 60 years, a workforce that held it without compromise, and a market that ultimately decided 60 years of unbroken precision was not worth the price difference between Sydney, Ohio and Osaka, Japan. Every week on this channel, we tell the stories of the American companies that built the machines the factory ran on and what the market did to them. If that history matters to you, subscribe. It takes 10 seconds. It keeps these stories coming. This one begins in Sydney, Ohio in 1909. Sydney, Ohio is not a city that appears in most American history books. It sits in Shelby County in the flat agricultural interior of western Ohio. Corn country, hog country, a landscape of grain elevators and county roads and small manufacturing plants that supplied the larger industrial cities an hour in every direction. Dayton to the south, Lima to the northwest, Columbus to the east. Sydney itself was a market town, a railroad junction, a place where the economy ran on what the factories made and what the farms grew in roughly equal measure. In 1909, that economy was about to add a third pillar. A group of local investors and machinists established the Monarch Machine Tool Company on the East Sabine side of Sydney that year in a building on Court Street that was modest even by the standards of a small Ohio manufacturing town. The founders were not industrialists in the Eastern sense, not the capitalized, connected machine tool entrepreneurs of Providence or Cincinnati or Springfield. They were practical men trained in the mechanical trades who understood that the American machine shop market had a gap in it. Production lathes, the workhorses of American manufacturing, were widely available and widely adequate. But the precision tool room lathe, the machine that a tool and die maker used to produce the gauges, the fixtures, the punches, and the dies that every other machine in the shop depended on, that machine, built to the accuracies the finest American tool rooms demanded, was not being built in western Ohio. Monarch set out to build it. The American context matters here. In 1909, the tool room lathe was the instrument of American manufacturing's intellectual core. The production machinist ran repetitive cuts on a standard engine lathe. The tool maker, the craftsman at the top of the shop floor hierarchy. The man who made the tools that made the parts worked on a tool room lathe. His machine had to hold tighter tolerances than any production lathe in the building. It had to repeat those tolerances across an entire shift day after day without drift. And it had to communicate its own accuracy to the man running it through the resistance of its hand wheels, the firmness of its ways, the absence of any play in its spindle, in a language that a skilled toolmaker could read without looking at a dial. No American builder in 1909 was delivering that machine at a price a mid-sized American tool shop could justify. Monarch's founders believed they could. The company's first significant commercial product was a line of precision engine lathes, introduced in the early 1910s, sold initially through independent machine tool dealers in Ohio, Indiana, and Michigan, the heartland of American precision parts manufacturing. The Thomas Register of American Manufacturers listed Monarch within its first decade of operation, establishing the company's visibility in the procurement channels that plant engineers and purchasing agents relied on to source machine tools. By the early 1920s, Monarch Lathes were selling into the expanding American automotive supply base, the hundreds of independent parts makers, tool shops, and stamping plants that fed the assembly lines in Detroit and Flint and Toledo without being owned by them. The list price of a Monarch precision lathe in the early 1920s ran between $800 and $1,400, depending on swing and bed length. Roughly $14,000 to $24,000 in today's money, a significant capital purchase for a small American job shop, but within reach of a toolroom foreman who could justify the accuracy premium to his plant manager. The machine tool dealer who represented Monarch in those years was not selling a commodity. He was selling a precision standard and the application engineering to prove it. When a dealer brought a Monarch into a shop and demonstrated its spindle accuracy against the shop's existing lathe, the difference was not a number on a specification sheet. It was visible in the finish on a test piece, measurable with a tenths reading indicator, and immediately legible to any trained machinist in the room. The first major institutional validation of Monarch's precision standard came from the American military procurement system. By the mid-1920s, Monarch lathes had entered government toolrooms, at arsenals, at naval ordnance facilities, at the precision instrument shops that the Army and Navy maintained to produce and maintain gauges and measuring equipment. A machine tool that passed government inspection and entered federal service carried an endorsement that no trade publication review could match. The Army did not buy imprecise toolroom lathes. If Monarch was in the arsenal, Monarch was accurate. By 1930, Monarch Machine Tool Company employed approximately 600 workers at its Sydney plant, a substantial fraction of the city's industrial workforce. The company had established a direct sales force to supplement its dealer network, sending application engineers into major industrial plants in Ohio, Michigan, Indiana, and Pennsylvania to demonstrate the Monarch standard against whatever the plant's toolroom was currently running. The approach was methodical, unglamorous, and effective. Monarch did not advertise precision. It demonstrated it. The stage was set for the machine that would define the company for the next 6 decades and place the name Monarch permanently in the vocabulary of American precision manufacturing. In 1937, Monarch Machine Tool Company introduced a lathe. That sentence does not sound like the beginning of a 60-year story. But the machine Monarch introduced that year, the Model 10 EE, designated for its 10-inch swing over the ways and its EE precision classification, the highest in the company's internal grading system, was not an incremental product improvement. It was a rethinking of what a toolroom lathe could be executed in cast iron and ground steel and hand-fitted bearings by assemblers in Sydney, Ohio, who understood that the difference between a precision machine and an accurate machine is not a matter of specification. It is a matter of discipline, the kind that cannot be automated, cannot be rushed, and cannot be purchased at a price point that makes financial sense unless the buyer understands exactly what he is paying for. The 10EE was at its core a turning machine, a lathe, which means it held a cylindrical workpiece in a rotating spindle and brought a cutting tool against it to remove material and create a precise shape. Every lathe does this. What separated the 10EE from every other lathe on the American market in 1937 was the architecture of its spindle, the quality of its ways, and the completeness of its drive system. The spindle, the rotating shaft at the heart of the headstock that holds and drives the workpiece, was ground to a runout tolerance of 0.0001 inches, 1/10,000th of an inch at the face. To understand what that number means in physical terms, a human hair is approximately 0.003 inches in diameter. The allowable deviation in the Monarch 10EE's spindle rotation was 1/30th the width of a human hair. Achieving that tolerance in production, not in a laboratory, not on a single prototype, but on every machine that left the Sydney plant, required spindle bearings that were hand-selected, hand-fitted, and hand-adjusted by assemblers who had been trained specifically for that task. There was no jig that automated the process. There was no shortcut that preserved the result. The assembler either fitted the bearing correctly or the machine did not leave the floor. The ways the precision ground flat and V-shaped surfaces on which the carriage traveled along the bed were ground and then hand-scraped to a flatness that a standard production lathe's ways never approached. Hand-scraping is an ancient craft. A skilled scraper uses a hardened blade to remove microscopic high spots from a cast iron surface, checking his work repeatedly against a precision granite surface plate until the bearing pattern, the distribution of contact points across the surface, meets a standard that can be verified but not easily described to someone who has never done it. It takes years to learn. It takes an hour per foot of travel to perform correctly. And it is the reason a Monarch 10 EE's carriage moved without detectable play, without any rocking, without any deviation from a perfectly straight line, a quality that a machinist felt in the first minute he ran the machine and never forgot. The drive system was the 10 EE's third distinguishing feature. Where most toolroom lathes of the era used a gearbox and belt arrangement that introduced vibration into the spindle at certain speeds, Monarch designed the 10EE with a dedicated motor generator set, a self-contained DC electrical drive that provided infinitely variable spindle speeds without the harmonic disturbances that gear change systems produced. The result was a surface finish quality on turned parts that was in 1937 and for decades afterward, the standard against which American toolroom practice measured itself. The 10EIE entered the American market at a list price of $2,650 in 1937, approximately $56,000 in today's money. At that price, the 10EEEI was not competing with production lathes. It was competing with the best Swiss and German toolroom lathes available in the American market, which ran $2,800 to $3,200, and with American competitors whose accuracy specifications were by Monarch's own testing and by the testimony of machinists who ran both measurably inferior. The Monarch dealer who put a 10EE on his floor and invited a tool and die foreman to run it for an afternoon was not asking the foreman to take the specification sheet on faith. He was asking him to feel the handwheel resistance, watch the surface finish on a test bar, and measure the repeatability of the carriage return with his own tenths reading indicator. The 10EE's distribution breakthrough came not through a single government contract or a major industrial standardization, but through something more durable: word of mouth among American toolmakers, a community that communicated horizontally across companies and cities through the informal networks of machinists, unions, trade school instructors, and the machine tool dealers who moved between plants and carried reputations with them. When a toolmaker at Pratt & Whitney's Hartford plant told a toolmaker at the Allison Engine Division in Indianapolis that the 10EE was the most accurate production lathe he had ever run, that endorsement carried more weight than any advertisement in American Machinist magazine. By the early 1940s, the 10EE had achieved something rare in American industrial commerce. It had become the assumed answer to a question. When a plant engineer needed to equip a precision toolroom, the question was not whether to specify a Monarch. It was how many. The American institutions that adopted the 10EE as their toolroom standard in its first decade of production read like a directory of American precision manufacturing at its peak. The U.S. Army Ordnance Corps placed Monarch 10EEs in the toolrooms at Springfield Armory in Massachusetts, Rock Island, Arsenal in Illinois, and Watervliet Arsenal in New York, the three primary centers of American small arms and artillery production. The U.S. Navy Bureau of Ordnance standardized on Monarch toolroom lathes for the precision instrument shops at the Naval Gun Factory in Washington, D.C., Pratt & Whitney Aircraft in East Hartford, Connecticut, builder of the R2800 double wasp engine that powered the F-6F Hellcat, the P-47 Thunderbolt, and the B-24 Liberator, equipped its toolroom with 10EEs. Allison Engine in Indianapolis, Wright Aeronautical in Paterson, New Jersey. The toolroom lathe that made the tooling that made the engines that flew the aircraft, it had a nameplate that said Sydney, Ohio. The nameplate on the headstock was not a city of origin. It was a tolerance standard. The Second World War did not create the Monarch 10EE's reputation. It confirmed it. When the United States entered the war in December 1941, the American manufacturing system faced a mobilization challenge that had no precedent in industrial history. The Army and Navy needed aircraft engines, artillery pieces, tank components, naval guns, bomb fuses, optical instruments, and small arms, all at volumes that American factories had never approached in peacetime, all to dimensional tolerances that could not be relaxed without compromising the performance of weapons in combat. The machine tools that produced those weapons had to be accurate. The tooling that set up those machine tools, the fixtures, the gauges, the jigs, the inspection instruments had to be more accurate still. And the lathes that produced that tooling had to be the most accurate machines in the building. In American factories mobilized for war production between 1942 and 1945, that machine was with a consistency that the procurement records of the period make unmistakable the Monarch 10EE. The U.S. Army Ordnance Corps issued Monarch toolroom lathes to precision toolrooms at Springfield Armory, Rock Island Arsenal, and Watervliet Arsenal under wartime procurement contracts that specified Monarch by name, not by category, not by generic specification, but by brand. When the Army's ordnance engineers wrote the toolroom equipment list for a new manufacturing facility, Monarch 10EE appeared as a line item, not as a type designation. That specificity in government procurement language is not routine. It reflects a determination made by the engineers who ran American weapons production that no equivalent substitute existed at the required accuracy level. At Springfield Armory in Springfield, Massachusetts, the facility that had produced American military rifles since 1794 and that was in the early 1940s, manufacturing the M1 Garand rifle at rates that would eventually reach 100,000 units per month, the precision toolroom that produced the gauges and inspection fixtures for M1 production ran on Monarch lathes. Every gauge that checked the headspace of an M1 receiver, every plug gauge that verified the dimensions of a gas cylinder, every thread gauge that inspected the barrel extension, those gauges were made on machines built in Sydney, Ohio. The arithmetic of that chain is worth following to its end. The M1 Garand was the primary American infantry rifle of the Second World War. Approximately 5.4 million were produced between 1936 and 1945. Every one of them was inspected with gauges whose accuracy traced back to the toolroom lathes that made them. The accuracy of those gauges determined whether a rifle functioned reliably in combat or failed at the moment a soldier needed it. The Monarch 10EE was not present on any battlefield, but its precision was present in every American rifle that was. The aerospace toolroom applications were equally consequential. Pratt & Whitney Aircraft's East Hartford plant, which produced the R2800 Double Wasp, the most powerful American air-cooled aircraft engine of the war, developing 2,000 horsepower, in its combat rating maintained a toolroom equipped with Monarch 10EEs to produce the precision fixtures and gauges that the R2800's manufacturing process required. The R2800 powered 18 distinct American combat aircraft, including the F-6F Hellcat, the P-47 Thunderbolt, and the F-4U Corsair. The tolerances on its internal components, the crankshaft journals, the master rod bearings, the supercharger impeller were held to specifications measured in 10,000ths of an inch. The tooling that held those components during machining was made on a Monarch. At Wright Aeronautical in Paterson, New Jersey, where the R3350 duplex Cyclone engine was produced, the engine that powered the B-29 Superfortress, the aircraft that carried the strategic bombing campaign against Japan, the same pattern held. The toolroom lathe at the center of Wright's precision fixture manufacturing was the Monarch 10EE. The fixtures made on that lathe held the R3350 cylinder barrels in position while they were bored to the tolerances that determined combustion efficiency and engine reliability. Every B-29 that flew a mission over Japan did so on engines whose manufacturing tolerances traced through the tooling chain to a toolroom in Paterson and a lathe built in Sydney, Ohio. The Monarch 10EE did not build those engines. It built the tools that built them. That distinction, the second-order role of the precision toolroom lathe in American manufacturing, is precisely what made the Monarch's contribution invisible to everyone except the toolmakers who understood it. Production workers counted parts. Plant managers counted shifts. The toolmaker counted 10,000ths, and the machine he counted them on was the 10EE. By 1945, Monarch Machine Tool Company employed approximately 1,100 workers at its Sydney plant. The company had delivered Monarch Lathes to military installations, aircraft plants, naval ordnance facilities, and precision instrument manufacturers across the continental United States. Its order backlog ran to 18 months. Its reputation in the American toolroom community was by every available measure: trade press coverage, government procurement specifications, machinist testimony without peer among American toolroom lathe builders. The war ended, the orders did not. The post-war American economy handed Monarch Machine Tool Company a market that its wartime production had in effect already won. The veterans who came home from the war and entered American manufacturing through the GI Bill's vocational training programs learned their trade on machines that their instructors had selected as the standard. In tool-making apprenticeship programs at trade schools in Ohio, Michigan, Indiana, and Pennsylvania, the machine at the center of the precision turning curriculum was with a consistency that reflected both institutional inertia and genuine conviction: the Monarch 10EE. An apprentice toolmaker who trained on a 10EE in 1948 and then walked into a job shop in Dayton or Detroit or Pittsburgh was walking into a building that in the majority of cases already had one. The machine he had learned on was the machine the shop ran. The skill was transferable because the standard was universal. That transferability was not accidental. Monarch had cultivated it deliberately through its relationship with the American vocational education system, placing demonstrator machines in trade schools, supporting instructor training programs, maintaining a technical service network that could respond to a school's maintenance question with the same urgency it applied to a production plant service call. The investment was not philanthropic. It was market development executed over decades at a level of institutional patience that reflected the company's understanding of how precision machine tool markets actually worked. You did not sell a toolroom lathe to a purchasing agent. You sold it to the toolmaker who would run it, and the toolmaker had learned what a precision lathe felt like before he had ever signed a purchase order. The post-war expansion of American aerospace manufacturing deepened Monarch's institutional position in ways that the wartime contracts had established but not fully realized. Boeing's Renton, Washington plant, which began producing the B-47 Stratojet in 1950 and transitioned to the B-52 Stratofortress in 1952, equipped its toolroom department with Monarch 10EEs as the standard for precision turning work on fixtures and tooling jigs. The Douglas Aircraft Plant in Long Beach, California, producing the DC-6 and later the DC-8, specified Monarch toolroom lathes for its fixture department. Lockheed's Burbank facility, home of the Skunk Works and the production line for the F-104 Starfighter, ran Monarch lathes in the toolroom that produced the precision fixtures for its airframe machining operations. The pattern was the same in every facility. The production floor ran whatever machine the procurement system had delivered at the best price. The toolroom ran Monarch. Because the toolroom was where accuracy mattered most, and in the American aerospace manufacturing community of the 1950s and 1960s, accuracy meant Monarch. General Motors' in-house toolrooms told the same story. At the Fisher Body Division's stamping plants in Flint, Michigan, where the body panels for Chevrolet, Buick, Pontiac, and Cadillac were stamped from sheet steel, the toolrooms that produced and maintained the stamping die's massive steel assemblies, whose surface geometry determined the shape of every panel that came off the press, ran Monarch toolroom lathes for the precision turning work that die maintenance required. At the Chevrolet engine plant in Flint, at the Buick Motor Division plant in the same city, at the Cadillac assembly plant in Detroit, the toolroom standard was through the 1950s and into the 1970s, the machine from Sydney, Ohio. By 1965, Monarch Machine Tool Company employed approximately 1,400 workers at its Sydney plant and maintained a network of independent machine tool dealers across the continental United States that numbered in the dozens. The company's annual production capacity ran to several hundred precision lathes per year, a modest number by the standards of high-volume machine tool builders, but not a number that Monarch had any interest in increasing at the cost of the quality standard that the 10EE's production process required. The company had resisted consistently and deliberately every commercial argument for relaxing its assembly tolerances in the interest of higher output. The 10EE took as long to build correctly as it took. No production incentive was worth the consequence of a Monarch leaving Sydney with a spindle that ran to less than its published specification. That discipline had a name inside the Sydney plant. The machinists and assemblers who worked on 10EE production called it simply the standard, not Monarch standard. The standard. as if there were only one and Monarch happened to be the company responsible for maintaining it. Now pause for a moment and consider what it felt like to run one. The Monarch 10 EE's carriage handwheel had a resistance that experienced toolmakers described in terms that were more sensory than mechanical. It was not heavy. It was not light. It was graduated the way a good physician's instrument is graduated, communicating information through the fingers that a number alone cannot convey. When a skilled machinist advanced the carriage into a cut on a 10 EE, the handwheel told him through the ground lead screw and the precisely fitted apron gearing whether the tool was cutting correctly or whether something the depth of cut. The tool geometry, the workpiece material, the spindle speed was not quite right. He did not need to look at a dial to know. He needed to pay attention to what his hand was telling him. The surface finish on a part turned on a 10 EE at the correct speed and feed with a properly ground tool had a quality that machinists called mirror. Not because it reflected like glass, but because it had a consistency of texture across its entire length that indicated the absence of vibration, the absence of chatter, the absence of any deviation in the spindle's rotation during the cut. Running your thumbnail across a correctly finished surface on a 10 EE part produced a sound, a faint uniform scraping that differed audibly from the broken irregular sound of a surface that had been cut on a machine with any play in its spindle bearings. The difference was not academic. It was the difference between a gauge that held its calibration for a year and one that drifted in a month. The smell of the cutting fluid on cast iron. The sound of the chip spiral coming off a high-speed steel tool at the right feed rate. Continuous uniform curling away from the cut in a single unbroken ribbon. The way the machine settled into a production run, its thermal expansion stabilizing after the first 20 minutes of operation, so that every subsequent part came off to the same dimension as the one before it. These are not descriptions that appear in a machine tool specification sheet. They are descriptions that appear in the memory of every toolmaker who ran a 10 EE for a career and who, when asked to describe the best machine he ever operated, paused for a moment before answering because the answer was not a decision. It was a recollection. The Monarch 10 EE remained through 1965 through 1975 through 1985, the standard against which American toolroom practice measured itself. 60 years of continuous production, the same spindle architecture, the same hand-fitted bearings, the same ground and scraped ways, the same tolerance that had been specified in 1937 and had never in the decades that followed been found wanting. The market, however, was about to ask a different question. And Monarch's answer, the only answer a company built on that standard could give, was about to cost it everything. The first warning arrived quietly. In 1968, Mori Seiki, a Japanese machine tool builder founded in Nagoya in 1948, 20 years after Monarch had already established its American reputation, entered the United States market with a line of engine lathes priced 25 to 35% below comparable American equipment. The machines were adequate. They were not Monarchs. American toolroom foremen who compared them against the 10 EE found the spindle accuracy acceptable for production work and insufficient for precision toolroom applications. The Mori Seiki did not threaten the Monarch 10 EE's position in the American toolroom. Not yet. Monarch's internal response was, by the standards of the period, reasonable. The company monitored the Japanese entry. It noted the price gap. It concluded not unreasonably that the customers who bought Mori Seiki lathes were not the customers who bought Monarch 10 EEs, that the precision toolroom market and the general production lathe market were sufficiently distinct that Japanese volume pricing in the lower tier would not migrate upward to threaten the precision tier where Monarch operated. That conclusion was correct in 1968. It was dangerously incomplete by 1975. The technology that changed the calculation was not a lathe. It was a controller. In 1972, a Japanese company called Fanuc Fuji Automatic Numerical Control began shipping CNC controllers, computer numerical control systems, at prices and in volumes that no American controller manufacturer had approached. A CNC controller is the electronic brain of a modern machine tool. The system that accepts a programmed sequence of axis movements, converts them to electrical commands, and directs the machine's servo motors to move the cutting tool or the workpiece to precise positions in three-dimensional space automatically without the machinist turning a handwheel for each individual positioning move. CNC did not replace the machinist's skill. It replaced his time, the hours of manual setup and positioning that a skilled machinist invested in every complex part before the first chip was cut. By 1978, Fanuc controlled more than 50% of the world market for CNC controllers. Its systems were standard equipment on Japanese machine tools. American shops that bought Japanese machines bought Fanuc controllers with them and learned to program in Fanuc's G-code language, a programming syntax that became through sheer market penetration the American shop floors assumed standard. When an American job shop hired a new CNC programmer in 1980, that programmer knew Fanuc G-code. He did not know Monarch's proprietary control language. He had never encountered it because the only machines that used it were Monarchs, and Monarchs were expensive and the shop he had trained at had bought Japanese. This was the Fanuc paradox, and it was lethal to American machine tool builders who had invested in their own control systems. Monarch had introduced CNC turning capability in the late 1970s with the Monarch 612 CNC Turning Center, a machine that applied CNC control to the precision spindle architecture of the 10EE lineage, offering American tool rooms the accuracy they expected from Monarch with the automation that CNC made possible. The 612 was by every technical measure Monarch could publish a superior machine to its Japanese competitors at equivalent specifications. Its spindle ran truer. Its thermal stability over a production shift was better documented. Its mechanical architecture reflected 60 years of precision lathe engineering in Sydney, Ohio. Its list price in 1979 was $62,000. 3 weeks after Monarch demonstrated the 612 at its Sydney open house in the fall of 1979, a Marubeni Corporation sales representative, Marubeni was one of the primary Japanese trading companies distributing machine tools in the American market, walked into a job shop in Dayton, Ohio, 40 miles south of Sydney, and demonstrated an Okuma LB 15 CNC turning center. The Okuma ran a Fanuc 6T controller. Every programmer in the Dayton shop already knew Fanuc 6T. The machine's spindle accuracy was measurably below the Monarch 612's specification. Its thermal stability over a long production shift was adequate, not exceptional. Its list price was $38,500. The shop foreman who made the decision had bought Monarch toolroom lathes for 22 years. He ordered 2 Okumas. He did not order them because they were better than the Monarch. He ordered them because the price difference, $23,500 per machine, $47,000 for the pair, covered his entire tooling budget for the following year. And because his programmers could be running production on the Okumas within a week of delivery without retraining, without learning a new control language, without the 2-week Monarch applications course that the Sydney factory recommended for new 612 owners. The Monarch 612 was the better machine. It lost the order on price and on the controller's programming language. 2 factors that had nothing to do with spindle accuracy and everything to do with the economics of running a small American job shop in 1979 when interest rates were approaching 15% and every capital purchase decision was being measured against a cash flow projection that left no room for premium pricing, however well justified. That order in Dayton was not an isolated event. It was a pattern. And the pattern repeated across hundreds of American job shops through 1979 and 1980 and 1981, produced numbers that the NMTBA, the National Machine Tool Builders Association, the trade organization whose annual statistics tracked the health of American machine tool manufacturing, recorded with a precision that matched nothing the industry had wanted to measure. United States metal cutting machine tool shipments peaked at $5.7 billion in 1980. By 1986, they had fallen to $1.9 billion, a decline of 67% in 6 years. The plants had not burned down. The machinists had not retired. The orders had gone to Osaka and Nagoya and increasingly to Seoul and Taichung. Monarch was not in the transfer line business. It was not building the machining centers that Japanese builders had captured most decisively. Its market, the precision toolroom lathe, the specialized CNC turning center for high-accuracy applications, was narrower and in principle more defensible than the general machine tool market that Japanese volume producers had overwhelmed. In principle, the first warning arrived quietly. In 1968, Mori Saeki, a Japanese machine tool builder founded in Nagoya in 1948, 20 years after Monarch had already established its American reputation, entered the United States market with a line of engine lathes priced 25 to 35% below comparable American equipment. The machines were adequate. They were not Monarchs. American toolroom foremen who compared them against the 10EE found the spindle accuracy acceptable for production work and insufficient for precision toolroom applications. The Morisaki did not threaten the Monarch 10EE's position in the American toolroom. Not yet. Monarch's internal response was by the standards of the period reasonable. The company monitored the Japanese entry. It noted the price gap. It concluded not unreasonably that the customers who bought Morisaki lathes were not the customers who bought Monarch 10EEs, that the precision toolroom market and the general production lathe market were sufficiently distinct that Japanese volume pricing in the lower tier would not migrate upward to threaten the precision tier where Monarch operated. That conclusion was correct in 1968. It was dangerously incomplete by 1975. The technology that changed the calculation was not a lathe, it was a controller. In 1972, a Japanese company called FANUC, Fuji Automatic Numerical Control, began shipping CNC controllers, computer numerical control systems, at prices and in volumes that no American controller manufacturer had approached. A CNC controller is the electronic brain of a modern machine tool. The system that accepts a programmed sequence of axis movements, converts them to electrical commands, and directs the machine's servo motors to move the cutting tool or the workpiece to precise positions in three-dimensional space automatically without the machinist turning a handwheel for each individual positioning move. CNC did not replace the machinist's skill. It replaced his time, the hours of manual setup and positioning that a skilled machinist invested in every complex part before the first chip was cut. By 1978, FANUC controlled more than 50% of the world market for CNC controllers. Its systems were standard equipment on Japanese machine tools. American shops that bought Japanese machines bought FANUC controllers with them and learned to program in FANUC's G-code language, a programming syntax that became, through sheer market penetration, the American shop floor's assumed standard. When an American job shop hired a new CNC programmer in 1980, that programmer knew FANUC G-code. He did not know Monarch's proprietary control language. He had never encountered it because the only machines that used it were Monarchs, and Monarchs were expensive and the shop he had trained at had bought Japanese. This was the FANUC paradox, and it was lethal to American machine tool builders who had invested in their own control systems. Monarch had introduced CNC turning capability in the late 1970s with the Monarch 612 CNC Turning Center, a machine that applied CNC control to the precision spindle architecture of the 10EE lineage, offering American toolrooms the accuracy they expected from Monarch with the automation that CNC made possible. The 612 was, by every technical measure, Monarch could publish a superior machine to its Japanese competitors at equivalent specifications. Its spindle ran truer. Its thermal stability over a production shift was better documented. Its mechanical architecture reflected 60 years of precision lathe engineering in Sydney, Ohio. Its list price in 1979 was $62,000. 3 weeks after Monarch demonstrated the 612 at its Sydney open house in the fall of 1979, a Marubeni Corporation sales representative, Marubeni was one of the primary Japanese trading companies distributing machine tools in the American market, walked into a job shop in Dayton, Ohio, 40 miles south of Sydney, and demonstrated an Okuma LB-15 CNC turning center. The Okuma ran a FANUC 6T controller. Every programmer in the Dayton shop already knew FANUC 6T. The machine's spindle accuracy was measurably below the Monarch 612's specification. Its thermal stability over a long production shift was adequate, not exceptional. Its list price was $38,500. The shop foreman who made the decision had bought Monarch toolroom lathes for 22 years. He ordered 2 Okumas. He did not order them because they were better than the Monarch. He ordered them because the price difference, $23,500 per machine, $47,000 for the pair, covered his entire tooling budget for the following year. And because his programmers could be running production on the Okumas within a week of delivery without retraining, without learning a new control language, without the 2-week Monarch applications course that the Sydney factory recommended for new 612 owners, the Monarch 612 was the better machine. It lost the order on price and on the controller's programming language, two factors that had nothing to do with spindle accuracy and everything to do with the economics of running a small American job shop in 1979 when interest rates were approaching 15%, and every capital purchase decision was being measured against a cash flow projection that left no room for premium pricing, however well justified. That order in Dayton was not an isolated event. It was a pattern, and the pattern repeated across hundreds of American job shops through 1979 and 1980 and 1981 produced numbers that the NMTBA, the National Machine Tool Builders Association, the trade organization whose annual statistics tracked the health of American machine tool manufacturing, recorded with a precision that matched nothing the industry had wanted to measure. United States metal cutting machine tool shipments peaked at $5.7 billion in 1980. By 1986, they had fallen to $1.9 billion, a decline of 67% in 6 years. The plants had not burned down, the machinists had not retired, the orders had gone to Osaka and Nagoya and increasingly to Seoul and Taichung. Monarch was not in the transfer line business. It was not building the machining centers that Japanese builders had captured most decisively. Its market, the precision tool room lathe, the specialized CNC turning center for high-accuracy applications, was narrower and in principle more defensible than the general machine tool market that Japanese volume producers had overwhelmed. In principle, the second front opened from a direction Monarch had not fully anticipated. It was not Japan. Japan had been visible since 1968. The second front was Taiwan, and it arrived in the mid-1980s with a proposition that was simpler, blunter, and in many respects more damaging to Monarch's remaining market position than anything the Japanese had offered. Taiwanese machine tool builders, Victor Taichung, YCM Femco, and a dozen smaller builders operating out of the Taichung Industrial District in central Taiwan had been producing conventional engine lathes for export since the early 1970s. By 1985, they were producing CNC turning centers. The machines were not precise by Monarch's standard. Their spindle runout ran to 0.0005 inches, 5 times the allowable deviation of a Monarch 10EE. Their ways were ground, not scraped. Their thermal stability over a production shift was adequate for parts tolerances in the range of plus or minus 1/1000th of an inch and inadequate for the tighter work that a precision tool room demanded. For approximately 70% of American job shops, adequate was sufficient. A Taiwanese CNC turning center entered the American market in 1986 at a list price between $18,000 and $24,000, distributed through American machine tool importers who had built their businesses on the Japanese volume trade and were now extending their lines down market to capture the price-sensitive segment that even the Japanese builders whose own prices had risen as the yen strengthened against the dollar following the 1985 Plaza Accord were beginning to price themselves out of. Against a $24,000 Taiwanese turning center, the Monarch 612 CNC at $62,000 required a justification that most American job shop owners in 1986 could not construct from their order books. The work that justified a Monarch's precision premium, the tight tolerance tool room, turning the precision fixture work, the gauge and die components that required spindle accuracy in the tenths, was a shrinking fraction of American job shop production. The Detroit automotive tool rooms that had been Monarch's most reliable institutional customers were contracting. General Motors had cut its in-house tool room workforce by 30% between 1979 and 1985, as it moved component sourcing offshore and reduced the scale of its internal manufacturing operations. Ford and Chrysler followed the same trajectory. The institutional buyers who had specified Monarch by name for 40 years were buying fewer machines of any kind. And there was one more force working against Monarch that no competitor had manufactured and no trade policy could address. It was the Monarch 10EE itself. By the mid-1980s, the American used machine tool market carried a deep, well-documented inventory of Monarch 10EEs in running condition. Industrial surplus dealers in Ohio, Michigan, Indiana, and Pennsylvania stocked them regularly. The machines were 30, 40, sometimes 50 years old. They had been maintained by toolmakers who understood their value and serviced them with the same care their original assemblers had applied in Sydney. A 1962 Monarch 10EE, properly maintained, held its original spindle tolerance. A 1955 Monarch 10EE, rebuilt by a competent machine tool rebuilder, held its original spindle tolerance. The used market price for a running 10EE in the mid-1980s ran between $3,500 and $7,000, one-tenth the price of a new Monarch CNC turning center, and for a small tool room doing conventional turning work entirely adequate. Monarch had built a machine so durable that the secondary market it created competed directly with its own new machine sales. A tool shop foreman who needed a precision tool room lathe in 1985 could buy a used 10EE from a surplus dealer in Toledo for $4,500 and have it running by the end of the week. Or he could spend $62,000 on a new Monarch 612 CNC, arrange financing at 12% interest, send his programmer to Sydney for 2 weeks of training on the proprietary control, and begin production in 6 weeks. For a shop doing conventional toolroom work, the work that most American precision tool shops still did, the used 10EE was not a compromise. It was the rational choice. The company that had defined American toolroom precision for half a century was being undercut by its own legacy. The acquisition followed. U.S. Industries, a New York-based conglomerate that assembled manufacturing businesses across multiple industrial sectors through the 1970s and 1980s, on a financial logic that valued asset base over engineering investment, acquired Monarch Machine Tool Company in the mid-1980s. The conglomerate model applied to a precision machine tool builder is a specific kind of mismatch. Precision machine tools are not mature businesses with stable markets and predictable cash flows. They are technology businesses in markets undergoing fundamental disruption, requiring continuous engineering investment to remain competitive at the precision tier where their pricing is justified. U.S. Industries did not make that investment. The Sydney engineering staff contracted. The R&D budget that had sustained the 10EE's continuous refinement over 5 decades was reduced. The product line did not advance. The workforce numbers tell the story with the economy of a machinist's logbook. Monarch employed approximately 1,400 workers in Sydney at its peak in the mid-1960s. By 1985, that number had fallen to approximately 800. By 1990, to under 500. By the mid-1990s, to fewer than 200. The machines still left the plant. The standard was still held by the assemblers who remained with the same discipline their predecessors had applied. But the order volume that had filled the Sydney plant for 60 years was no longer there to fill it. Dainichi, a Japanese precision lathe builder, acquired the Monarch name and remaining operations in the early 1990s. The acquisition did not restore Sydney's production volume. It transferred the nameplate to a different ownership structure without resolving the underlying market reality. American shops had stopped buying new precision toolroom lathes at Monarch prices. The Japanese competition had captured the CNC turning center market. The Taiwanese builders had captured the price-sensitive segment below it. The used 10EE market had absorbed the residual demand for conventional precision turning. There was nothing left to sell into. The Sydney plant produced its last American-built Monarch lathe in the late 1990s. The building did not close dramatically. There was no announcement, no final ceremony. The production line wound down. The remaining workforce was let go in stages with the quiet procedural grief of an industrial, closing in a small Ohio city that had seen enough of them to know how they ended. The equipment was inventoried. The auction date was set. In the fall of 2000, the doors opened. The machines went first, then the tooling, then the fixtures, then the precision ground surface plates that the assembly department had used for 60 years to verify the accuracy of the machines they built. By the second day, the floor was empty. The overhead cranes were still. The fluorescent lights buzzed in the silence above a concrete floor that had supported the weight of 10,000 precision lathes over 9 decades. The last thing to leave was the nameplate inventory. Stamped steel, Sydney, Ohio. Nobody bought those. The Monarch 10EE did not disappear when the Sydney plant closed. That is the first and most important thing to understand about what Monarch left behind. The machines were built to outlast the company that made them, not by intention, but by consequence. The consequence of a precision standard that did not permit shortcuts in materials and assembly or in the quality of the cast iron that formed the bed and headstock of every 10EE that left Sydney. cast iron that dense ways that accurately ground spindle bearings that carefully fitted do not wear out on a human timescale when they are properly maintained. They wear slowly, measurably correctably. A Monarch 10EE that was assembled in Sydney, Ohio in 1955 and maintained by a competent toolmaker through the following decades is in 2025 still capable of holding its original spindle tolerance, not as a curiosity, not as a museum piece, but as a working precision instrument. Thousands of them are still working. The American used machine tool market for Monarch 10EEs is by the standards of a product whose manufacturer closed its doors 25 years ago, remarkably active. On any given week, a search of industrial surplus listings, eBay Machinio, the auction platforms that serve the American machine tool, secondary market returns between 15 and 40. Monarch 10EEs offered for sale in conditions ranging from rough project machines at $800 to fully rebuilt, freshly painted, electrically updated lathes at $8,000 to $12,000. The buyers are not collectors in the conventional sense. They are working machinists, small tool shops, prototype shops, and one-man precision machining operations whose owners understand that a properly maintained Monarch 10EE delivers accuracy that a new import lathe at twice the price cannot match for the specific categories of work: close tolerance, turning precision thread, cutting fine finish work on hardened steel that define a toolroom, lathe's purpose. The community that surrounds these machines is for an online forum unusually serious. Practicalmachinist.com is the primary online gathering point for American machinists who work with and maintain vintage American machine tools. The forum's Monarch 10EE thread, which has been active for more than 15 years, runs to several hundred pages of accumulated technical discussion. Electrical diagrams for the 10EE's motor generator drive system. Bearing specifications for every headstock variant produced between 1937 and the 1990s. Procedure guides for way scraping and spindle bearing adjustment written by machinists who learned the techniques from men who had learned them in Sydney. Sources for replacement parts, the lead screws, the apron gears, the spindle bearings that are no longer manufactured but can be sourced, remade, or substituted by machinists who know what they are looking for. The Vintage Machinery website, vintagemachinery.org, maintains a digital archive of Monarch machine tool catalogs, technical manuals, parts lists, and factory photographs extending back to the company's early decades. The archive is searchable by model number, by year, by document type. A machinist in rural Montana who acquires a Monarch 10EE from an estate sale can download the original factory manual for his specific serial number, range the electrical schematic for his drive system, and the factory inspection report format that Monarch's quality department used to verify each machine before shipment. The knowledge that Monarch's engineering department accumulated over 60 years of continuous 10EE production has not been lost. It has been digitized, distributed, and maintained by the community of machinists who consider that knowledge worth preserving. The American Society of Mechanical Engineers designated the Monarch 10EE Historic Mechanical Engineering Landmark, a recognition extended to machines and systems that made a demonstrable contribution to the development of American mechanical engineering practice. The designation is not honorary. It reflects a formal evaluation of the 10EE's technical significance. The motor generator drive system that provided vibration-free variable speed control. In 1937, the spindle bearing architecture that achieved 0.0001-inch runout in production. The hand-scraping methodology that the Sydney plant maintained as standard practice decades after competing builders had abandoned it for ground-only ways. The professional categories that Monarch's precision standards sustained have not survived as well as the machines themselves. The machine tool rebuilder, the craftsman who disassembled worn American lathes, reground or rescraped their ways, replaced their spindle bearings, and returned them to original factory tolerance, was a recognized American industrial trade through the 1980s. Rebuilding shops operated in every major American manufacturing city. Their practitioners held skills hand-scraping, spindle-bearing, fitting, lead screw assessment and replacement that required years of apprenticeship to acquire and that could not be learned from a manual or a video. When Japanese machines arrived at prices below the cost of rebuilding an equivalent American machine, the economics of the rebuilding trade collapsed. The shops closed. The craftsmen retired without training successors. the skills did not transfer to the next generation of American machinists because the next generation of American machinists was trained on CNC equipment that did not require those skills. Today, a machinist who can correctly hand-scrape the ways of a Monarch 10EE and fit its spindle bearings to the original factory tolerance is a rare individual. The Practical Machinist Forum can name them. There are perhaps a dozen in the continental United States whose skill level the forum's membership would endorse without qualification. A dozen craftsmen maintaining a skill that once employed hundreds across Ohio and Michigan and Indiana and Pennsylvania. The skill is not extinct. It is approaching it. The surprise in Monarch's legacy lies not in what was lost, but in what traveled. The Monarch 10EE's precision spindle bearing architecture, the specific geometry of the bearing, housing the preload methodology, the thermal compensation design that allowed the spindle to maintain its accuracy as the machine warmed through a production shift, was documented in technical papers published by the National Machine Tool Builders Association in the 1940s and 1950s. Those papers were available to any machine tool builder in any country. Japanese precision lathe builders who were systematically studying American machine tool design as they developed their own product lines in the 1960s and 1970s had access to them. Several Japanese builders incorporated design principles derived from the 10EE's spindle architecture into their own high-accuracy lathe lines. The machine that displaced the Monarch 10EE in the American Precision Tool Room was in part an engineering descendant of the machine it replaced. Sydney, Ohio taught Nagoya what a precision spindle was. Nagoya taught the American market that it could buy that precision at a lower price. The student had learned the lesson completely enough to make the teacher unnecessary. That is not a story of theft. It is a story of diffusion, the way technical knowledge moves through industrial economies, regardless of the commercial consequences for the companies that generated it. Monarch's engineers did not give their spindle architecture away. They published it as American engineers published everything they knew in the institutional confidence that American manufacturing's lead was wide enough to absorb the knowledge transfer without consequence. They were right about the knowledge, they were wrong about the lead. There is one more thing worth knowing about the Monarch 10EE. The machine has been in continuous use in the American precision machining community for longer than most American manufacturing companies have existed. Lathes built in Sydney, Ohio in the 1940s are producing precision parts in American tool shops today. Their spindles are running, their ways are holding, their hand wheels are turning under the hands of machinists who may have learned on them or whose fathers learned on them, or who found one in a surplus auction and spent 6 months restoring it because they understood in the way that precision machinery communicates its own worth to the people who know how to use it, that what they had found was not old equipment, it was a standard. In the back corner of a small tool and die shop in Sydney, Ohio, 2 blocks from the building where it was assembled in 1962, there is a Monarch 10EE tool room, lathe serial number 17431. The ways have been scraped twice in 60 years. The motor generator set was rebuilt in 1989 by an electrician who had worked at the Monarch plant and knew the system from the inside. The spindle still runs to 1/10 of a thousandth. The chip tray still carries the smell of cutting fluid on cast iron that every machinist who ever ran one of these machines would recognize in the dark. The nameplate on the headstock still reads Sydney, Ohio. The company that put it there has not existed for 25 years. The machine has not noticed. Every week on this channel, we tell the stories of the companies that built these machines and what it cost to build them and what it cost to lose them. If that history matters to you, subscribe. Leave a comment below about the first precision lathe you ever ran or the one you still have in your shop. The machines remember. So do we.